Hi, Mr. Simmons here, and I'm going to go through P9.4 Analysing motion graphs with you. I'm going to go through the answers to the textbook questions. So, learning objectives for this are how to calculate acceleration from a velocity time graph, and also for higher tier, how to calculate distance from a velocity time graph, and how to calculate speed from a distance time graph, where the speed is constant and where the speed is changing. So I've put on here a few key points which are all taken from the textbook. The speed of an object moving at constant speed is given by the gradient of the line on its distance time graph. So the steeper the gradient or slope of the line, the faster the object is going. That's on a distance time graph. The acceleration of an object is given by the gradient of the line on its velocity time graph. So the study tip over here, make sure that you know whether you are dealing with a distance time graph or a velocity time graph. The gradients of these two types of graph represent different quantities. Then for higher tier, the distance travelled by an object is given by the area under the line on its velocity time graph, and the speed at any instant in time of an object moving at changing speed is given by the gradient of the tangent to the line on its distance time graph. The two equations that you need to know here are that the gradient of the line equals the height of the triangle divided by the base of the triangle, and that the acceleration is the change of velocity divided by the time taken. So, question 1. Determine the speed of the object shown on the graph in figure 1. So I've put figure 1 on here, and we need to use the information in the key points and the equations. So the speed of an object moving at constant speed is given by the gradient of the line on its distance time graph, and the gradient of the line equals the height of the triangle divided by the base of the triangle. So those are the two key bits of information we need to use to work this out. So our gradient is given by the vertical change divided by the horizontal change. So here's our triangle here, I'm highlighting. Now the vertical change, the line here goes up to, it's actually slightly below the maximum on the scale. So the maximum on the scale going across the top here is 160, but our line is slightly below that. So it actually tracks across. If you draw a straight line nice and neatly with a ruler, it will track across to this point here, directly halfway between that line and the 160. Now this is 120, this is 160, so that halfway point there would be 140, and our line comes up to halfway between the 140 and the 160, so it is at 150. So in our equation, the height of the triangle, this height here, is 150 meters per second. So our gradient equals 150 divided by the base of the triangle, which given along the bottom here goes from 0 to 10. So our gradient is 150 divided by 10, which is 15, and our gradient is the speed of the object, so our gradient is going to be in units of meters per second. So the gradient is 15 meters per second, that's the speed of the object. So here's figure 2. You can see for a moving object with changing speed, the distance time graph is not a straight line. The red line in figure 2 shows an example. So our line here is curving upwards, so at the beginning it's quite a shallow gradient, and by the end it's quite a steep gradient. So as it says down here in figure 2, the gradient of the line increases, so the object's speed must have increased. So for B, all we need to say is that the speed increases, the object accelerates. And we could say it accelerates from rest. because at the beginning the object was not moving. Question 2. The graph in figure 4 shows how the velocity of the cyclist on a straight road changes with time. A. Describe the motion of the cyclist. So all we need to do here is look at the graph and describe what the graph is showing us. So we can see that we've got a positive gradient here and it's in a straight line, and then we've got a negative gradient here in a straight line. So going back to our information at the start, the gradient of the line is the height of the triangle divided by the base of the triangle, and the acceleration of an object is given by the gradient of the line on its velocity time graph. Now this is a velocity time graph. We've got velocity in meters per second on the y-axis and time in seconds on the x-axis. So what we can see is for the first part of the graph where we've got a positive gradient, then that is showing a constant, or what we call a uniform acceleration. So for A, describing the motion of the cyclist has uniform acceleration from 0 to 40 seconds, then uniform deceleration from 40 to 60 seconds. Part B, use the graph in figure 4 to determine the acceleration of the cyclist and the distance travelled in the first 40 seconds, the following 20 seconds. So for the first 40 seconds, so we're looking at the part of the graph where we have the positive gradient showing the constant or uniform acceleration here. To work out the acceleration, we do the gradient of that graph, and so that is going to be 8 for the velocity. The maximum velocity reached is 8, so acceleration A equals 8 divided by 40, which is the number of seconds down the bottom, so that gives us 0.2 meters per second squared. Remember that for acceleration the units are meters per second squared, whereas for speed or velocity they're just meters per second. And then for the distance travelled in the first 40 seconds, so now we're looking at working out the area of this triangle here underneath the line. The equation for area of a triangle is equal to half times the base times the height. So in this case our base is 40 seconds, so the distance travelled, which remember is the symbol s, is a half times the base, which is 40, times the height, and the height of the triangle you can see on the graph is 8. So our distance travelled therefore is a half times 40 times 8, which equals 160 meters. And then for the following 20 seconds, so acceleration again, remember, is the gradient, and this time the gradient is negative. So we're looking now at this part, the line sloping downwards showing that it's negative, and we need to work out the area under that part of the line. So again, using this, the equation for gradient is the vertical divided by the horizontal, so that's just going to be, it's negative 8 because we're going from 8 down to 0, so acceleration is negative 8 divided by, this time the time taken going along the bottom here, goes from 40 to 60, and so it's negative 8 divided by 60 minus 40, which is 20. 60 minus 40 is 20, so our acceleration, negative 8 divided by 20, gives us negative 0.4 meters per second squared. And then moving on to the distance, that's the area of the triangle, so the distance S is a half times the base times the height. The base was 20, so it's a half times 20, and the height was 8. Don't need to worry about negatives when we're doing distance. So a half times 20 times 8 gives us 80 meters. Part C says calculate the average speed of the cyclist over the journey. Now we need to use the equation here that average speed equals distance divided by time. Now our total distance for the average is the area under both of those triangles. So it's going to be 160 plus 80. So our distance that gives us 240 meters. And then our total time is of course 60 seconds going all the way along the bottom of the graph. So our average speed V is 240 divided by 60, which gives us 4 meters per second. So for question 3, this doesn't work very well trying to draw a graph on the screen because it's not accurate enough. So I'm going to try and show you this on paper instead, and then I'll come back to this screen just to do the working out. Okay, so we're going to draw a graph of velocity against time from these motorcycle test results. So time is going to go on the x-axis and velocity is going to go on the y-axis. So I'm going to use a scale on the x-axis of 5 seconds for every 2 centimetres going up. So from 0, that'll be 5, 10, 15, 20, 25, 30. So we'll just mark those on, 0, 5, and so on. And not forgetting to label. And then on the vertical, the y-axis is going to be velocity in meters per second, and I'm going to use the same sort of scale, so 2 centimeters for every 5 meters per second going up here. So it's going to be 5, 10, 15, 20, 25, 30, 35 and up to 40. And again, not forgetting to label the axis. Velocity in meters per second. So my first point on the graph is at 0 for both time and velocity. The second point is at 5 seconds, and that is a velocity of 10 meters per second. So there's 5 seconds, there's 10 meters per second, so my first point goes there. The second one is at 10 seconds and 20 meters per second, so here's 10, go up to 20. The third point is at 15 seconds and 30 meters per second, so going up from 15, there's 30. Then the next one is at 20 seconds and 40 meters per second, so I'm just going to move this down a little so you can see to the top here. So from 20 seconds going up to 40 on my y-axis scale. And then the next two for 25 seconds and for 30 seconds are also at 40 meters per second like that. So then I've got to draw a line through these points. So it starts at 0. It's going to go straight through the crosses initially in a straight line diagonally upwards. Just move this down a little so you can see. And then it changes to a constant velocity of 40 meters per second for the last 2 points like that. So there's my graph. Now that's question 3a. 3b says calculate the initial acceleration of the motorcycle, and to do that we need to work out the gradient of this graph. So what I need to do is I need to draw a dotted line. So by initial acceleration, we could go at any point, but I'm going to make it as big as possible. Whenever you're doing a gradient, the bigger the triangle you draw, the more accurate your result will be. So I'm going to go right from the top of the diagonal part of the graph, and I'm going to draw down to the x-axis, like that, to make a triangle. And then I need to use the equation A for acceleration is v minus u for change in velocity divided by time. So my v minus u, this is the vertical change on my graph, so it's gone from 0 at the bottom up to 40 at the top. So my vertical change to work out my gradient is 40 meters per second, and then the time going along the x-axis is from 0 to 20, so the change in time is 20 seconds. So I'll show you the calculation, the working out back on the screen in a moment. So for B then, from our graph, calculate the initial acceleration of the motorcycle. Our acceleration is 40 divided by 20, and that gives us 2 meters per second squared. So question C says calculate how far the motorcycle moved in the first 20 seconds and in the following 10 seconds. So the first 20 seconds, the distance covered, remember, is the area under the line. So for the first 20 seconds, the distance covered is the area of this triangle here that I've drawn to calculate the gradient, which was the acceleration for part B. So that's covered by the formula. Distance, the area of a triangle, is half times the base of the triangle times the perpendicular height of the triangle. So it's just a half times 20, which is the base of the triangle, times 40, which is the height of the triangle. Then the distance in the following 10 seconds is going to be given by the area of the rectangle under this last part of the graph. So if you imagine a rectangle with a line drawn down here all the way to the bottom, so it's the area of the rectangle is just one side multiplied by the other, so it's 30 minus 20 will give us 10 times the height of that rectangle, which is 40. So 10 times 40 will give us the distance covered under that, and then I just need to add the two of them together. So C part 1, for the first 20 seconds, the area of our triangle is equal to half times the base times the height, which equals half times 20 times 40, which gives us 400 meters. And for part 2, the following 10 seconds, it's the area now of the rectangle, which equals 30 minus 20 times 40, which gives us 400 meters again. Okay, so finally question 4. Use table 1, which is what we got the graph from initially, and the equation v squared equals u squared plus 2as. So v squared equals u squared plus 2as. So v squared is our final velocity, and we need to work this out as if it had kept the same acceleration as it had during the first 20 seconds. So this is what we're trying to find out. So it's going to equal u squared, that's our initial velocity, and our initial velocity, you can see in the table, is 0. So initially, time at 0 velocity is 0. So 0 squared is just 0, plus 2 times the acceleration as it had during the first 20 seconds was 2 meters per second. That was our answer to 3b. And then multiplied again by the distance, and the distance, it says after 1 kilometer from the start. So 1 kilometer, I'll do this up here, 1 kilometer equals 1,000 meters, and we need to make sure we stick to the standard units. We don't use prefixes when we're doing the calculation. So it's 0 plus 2 times 2 times 1,000 meters, and that will then give us our answer for what v squared is. So v squared is therefore 4,000. But we want to actually work out what v is, the velocity of the motorcycle, not the velocity squared. So if v squared is 4,000, then v will be the square root of 4,000, which gives us 63.2 meters per second, rounded to 3 significant figures. That's it. Well done, and keep safe.